All right, so I want to introduce you to the world of vector projections. We're going to need these concepts as we move along in the course and build some theory, but you'll also run into them in a lot of application settings like physics or engineering, those kinds of things. So what's the setup? Well, let's start out with two vectors, and we'll call this one B, and let's make that one A. And I didn't let the auto line adjustment for B. Let's redo it so that it looks nice. There it is. Okay. So what I want to do is I want to project B onto A. Now, I'm going to show you how to do that and what that means, but I would love for you to pause the video for a moment and just think visually. Pull out a piece of paper and doodle. What do you think it should mean to project B onto A? Okay. So here's the idea. I want to drop a perpendicular from the tip of B down to A, but I want to do so that when it hits, I form a 90-degree angle. So something like that right there. I don't want to do that because that's not 90 degrees or that, but when I do it this way, then I'm left with a 90-degree angle right there. And so that's what I want to do. That's the perpendicular that I'm dropping. And now what's the projection? Well, the projection is this new vector right here that starts where A starts and it ends where my perpendicular fell. And so we write that vector that I just wrote down, we call it the vector projection of B onto A. The writing is a little bit hard, I guess. We write it where A is the subscript and then B is sort of big. So we're projecting B onto A. So you're going to need to make sure that you remember what this means and which one is getting projected, and then try to remember the picture as well. So I'm going to show you the formulas for how to do this, and they're just formulas. If you know the formulas, you can do it. But I would like to make sure that we understand the notion by drawing you a couple other pictures of cases that pop up. So the picture that we drew right here is in the case when the angle between A and B is acute. Let's draw a similar picture for when the angle between them is actually obtuse. So I think I had A longer, and then let's do B, something like that. So here's my A, here's my B. Well, you know, you might try to like slice it this way. Ooh, that's going to be really hard to get a perpendicular that way. The idea is, no, don't do it that way. Take and flip A. You can do that. You can flip A this way. I can't seem to draw straight. Let me try again. There we go. It's been a long day. Okay, so I'm drawing negative A, and then I can project the tip of B down to negative A, and I get that. And so that's the idea here, that you can project on this side, and then this vector, each time that I draw the projection, it's going to be the green vector. So this vector is the projection, the vector projection. You know what? I shouldn't draw the arrows because then you're going to get confused. But same thing. So this, in this picture, that vector is the vector projection of B onto A. And then similarly, if I want to go over here, and I want to do the case when B is longer, let's say. So here I'm going to flip the roles. So let's make B the long one, and A, oops, let's let it auto straighten out here. A is the short one. What do? Kind of hard to, you know, draw a 90 that intersects. Well, you just extend A out a little bit, right? You just extend, imagine A extending, and now you can drop that perpendicular off of B and form a 90-degree angle, and that allows you to conclude that this vector right here is actually the vector projection. So those are some of the different pictures, and I would really encourage you to take a few moments and let this notion sink in, because I want you to be able to recognize, oh, that's a projection of this onto that visually. That's just as important as the formulas. All right, well, let's continue. I think I'll do a little bit more before I break the video. So the key observation is the following, is that the vector projection of B onto A is just a scalar multiple of which vector? You tell me. I guess you can't tell me, but you can say it out loud. It's a scalar multiple of A, right? We're multiplying the length of A. Here I'm shortening A. I'm shortening A and putting it here. Here I'm flipping A and then shortening it. Here I'm lengthening A. But the point is, I'm just scaling A. That's all this is. So somehow vector projections mathematically aren't that big of a deal because you're just scaling the length of a vector. It's just the question is how much do you scale it by? So I want to do some computing with you, and I want to, for the sake of simplicity, I'm going to assume we're in the first picture case. The formula that I'm going to come up with works in all of these cases because there's an absolute value that sort of shows up that I'm going to not write because I'm in this case. Anyway, let me show you where this comes from. So if we could figure out what the length of the vector projection of B onto A was, let's say that we could, and let's call it C. So let's let C equals the length of the vector projection of B onto A. Okay, so C is just this length right there. Again, I'm working in this case, so I'm assuming here that the angle between A and B is acute. All right, so let's do that. So C is the length of the vector projection, and let's realize that if I know that, then I claim that the vector projection of A onto B I can write as this C times the vector A over the length of A. Now, why is that? Well, A over length A gives me a unit vector pointing in the direction of A, and then C gives me the length of the vector projection. So this part keeps the direction of A, and this part allows you to scale the length to whatever you want. So knowing this little connection here is going to be the key to finding a formula for what's going on. So let's break this video here before I go on any longer. In the next video, we're going to come up with a formula. We'll do an example. We'll call it a lecture.